Okay, let's please review what we did last time. We started, can I have your attention please everyone? We started with capacitors and capacitance, okay? What's a capacitor? What is it made of? Good, two metals, so two conductors. They could be any shape, they could be sheets, or they could be any other shape in general. So we usually take the two sheets because it's the simplest shape available. So that's the capacitor. There's two conductors. Its job is to hold charge, is to store charge. Okay, that was that. And then capacitance is the quantity given the symbol C, and it's defined as the charge over the potential difference between the two conductors. In short, sometimes we just write Q over V, all right? So if you see Q over V or Q over delta V, it's the same thing. So you have, in general, you have here is a conductor 1, and here is a conductor 2. On here, maybe there is a plus Q, and here there is a minus Q. And so it's just Q divided by the potential difference between the two conductors. Now, units, and then we will talk about review parallel plates. Units. A farad, 1F. And it's a coulomb per volt. So that's a farad, 1 coulomb per volt. Sometimes people just say, or 1F, okay, 1 farad, 1 F. All right, sounds good? So that's the farad. Now, let's talk about specific shapes and what the capacitance is. So for parallel plates, specifically for parallel plates, you have a plate here and another plate here, and they might have, this one might have some charges, might be positive, this one would be minus, so plus Q or minus Q. The distance between the two plates is D, right? Distance between the plates is D. So the potential difference between the plates, delta V, is just D, and it is the electric field between the two plates times the distance, right? And the electric field between two sheets is the charge density over the area. Right? The electric field between two sheets is it's the charge sigma over epsilon naught. Sorry, I'm ahead of myself. And then sigma is the charge over area. So it is sigma is the charge over the area. Still have the epsilon naught. Still have the d. What do we mean by area? These are plates. They extend this way. So this one has a plate, an area A, and this one has another area A. That way. Those are two plates. So the capacitance is Q over V, or delta V absolute value. And it's just, if you divide Q over this, the Q cancels and the fraction flips, and you get epsilon naught times the area over. Yes, we got this last time. Now, I wanted you to remember that capacitance is always a geometric quantity that, in this case, depends on the area of the plates and the distance between the two plates. So once you make a capacitor, it has a certain amount of capacitance, regardless whether you charge it or you don't charge it. And I gave the example of this bottle. It holds half a liter, regardless whether it's full or empty. It's still half a liter. So that's our capacitor. Okay. We did the cylindrical capacitor last time. No, we did, right? And I think we stopped at the spherical capacitor, which is the one we did not do. So I would like to go over the spherical. Cylindrical, we can review it, or we can go over it during discussion. So So spherical capacitor is made of two metal or two conducting sheets or two conducting shells. You will have this shell has an inner has a radius A, and this shell has a radius B. And the question is, what's the capacitance of these? These are spherical shells, right? This is just a cross section. They're actually three-dimensional spheres, which is looking inside. The way you do it is it's Q over V. You have to find the potential difference between the two shells, between the inner one and the outer one, and then you Q over that. So how do you go about doing that? So let's say you call this one plus, and this one will have minus, and equal but minus charge. So here is a plus Q, and here that's a minus. The potential difference between the two shells, by definition, is delta B is equal to minus the integral from A to B of E dot E dot, right? That's the definition of the potential difference. And then, what's the electric field between the two shells in terms of Q? Let's review. What's the electric field inside? Zero. Yeah. By spherical symmetry. Zero. In here, it's not zero. It's what?
It's like a positive.
It's like a point charge, right? So Q over 4 pi epsilon naught over R squared. And then here?
Zero.
It would be zero. So you can use Gauss's law to prove all of these. So the relevant part is here. So I have minus and then Q over 4 pi epsilon naught. These are the constants. And then the 1 over R squared is here. The dot product gets rid of the vectors from A to B. The integral of 1 over R squared is minus 1 over R. There is a minus sign, so it just becomes 1 over R. You substitute B and A, you get 1 over B minus 1 over A, right? So you get Q over 4 pi epsilon naught becomes 1 over B minus 1 over A. Make a common denominator, so you get delta B is equal to Q over 4 pi epsilon naught. You get A minus B over A minus B. Okay. Now, is this quantity here positive or negative? Negative because? A is less than B, yeah. In the definition of capacitance, I want it to be positive, right? I want the absolute value of V. So what's the absolute value of V becomes? Yeah. What's the absolute value of -5? It's negative 5, right? So it's positive 5. So you put a minus sign in front, or just switch the B and the A. So you get Q over 4 pi B minus A over A times B. And so the capacitance, which is Q over V. So if you do Q divided by all this, Q cancels and fraction gets 4 pi A times B divided by B minus A. So this formula applies for spherical capacitance, right? A spherical capacitor. That's what it applies to. Another note, again, look at capacitance. What does it depend on? You got 4 pi epsilon naught. A and B are the radii, right? The radius of the inner. So the geometry of the two spheres. So again, it's a geometric form. You construct it, and therefore you have it. That's that. Then, how do we charge a capacitor? You can physically charge it, but then it's not easy. So charging a capacitor. and then the energy stored inside the capacitor. So here is a capacitor. So it's not charged. So how do we charge it? We've got a capacitor, and we ask, how do we charge it up? So you start, I want this one to have an equal but minus charge, right? So the way you do it is, you can go to infinity and grab charges, but you don't have to. You can just take pluses from this plate and place them on this one. So if I remove a plus charge from this one and place it here, this plate becomes plus, but this one lost a plus, so it becomes negative. They started having equal amounts of pluses and minuses, but when you start removing. Now the problem is this, you can't by hand grab the pluses. So you need somebody to do it, and that's the job of a battery. So the symbol for a capacitor in the circuit would be just two plates. This is called a wire. This is a wire. Wires are conductors. Plates are also conductors. And then you will put a battery. So before I discuss the battery, I want to discuss something else. But I will just write down how battery looks like in a circuit. It looks like this. So this is the positive side of the battery, and then this is the minus side of the battery, so it looks like that. Okay. But before we discuss any details here, since we did not do the equipotentials in the lab for this section, so I want to discuss equipotential surfaces before I go on. So conductors are equipotential surfaces. Conductors are equipotential surfaces. Why is that? I'm saying a conductor will have the same potential throughout. So here is a conductor. So take any shape of a conductor. It doesn't have to look like this. So I'm trying to draw an arbitrary thing. And always my arbitrary thing looks the same, so it's not arbitrary. So that's a conductor. Okay? We said the electric field inside the conductor is always zero. And then if there is an electric field, if there is a net charge, it would be on the surface of the conductor. And the electric field on the conductor, at the surface of the conductor, is always perpendicular to the conductor. Remember that? Electric fields are always, it's zero here, but if there is an electric field, it's always going to be perpendicular to the surface of the conductor. Always makes a 90-degree angle. So this is the electric field. Electric field always makes a 90-degree angle. Now, what's the potential? Let's say I have point 1 and point 2. Point A and point B. What's the potential difference between this point and this point? By definition, the potential difference between A and B would be VB minus VA, which is equal to minus the integral E dot ds or dr. I'll put ds here because I'm on the surface of it from A to B. Now, the electric field is always perpendicular. You get from A to B, here is ds. So what angle do they make with each other? 90. Yeah, so the dot product would just be 0. E dot ds is going to be 0. So the right-hand side is just going to be 0. That means the potential at point B would equal to the potential at point A. So a conductor is an equipotential surface. Conductors are equipotential surfaces. So anywhere on the conductor, it would be equipotential. And if I connect this conductor with another conductor using a conductor, it will still be equipotential. So this is the whole thing. The charges will have to distribute somehow to make this equipotential. So why is this relevant to here? This is a conductor. Wires are conductors, and the terminals of the battery are also conductors. Okay? So what I'm saying is, if I have a battery, before we discuss what the battery does, so just imagine you have the general, let's say you have a 12-volt battery, car battery. So this side is 12, this one is 0. So 12-volt battery means there is a potential difference between the two terminals, between one end and the other, of 12. Okay. So if this is 12, this whole thing has to still be 12, including this one. And then, yeah, and then I will talk about how the battery is doing, well, partially, how the battery moves the charges. Okay. So how does the battery move the charges from here to here? So here's the battery. Looks like this. I'm going to exaggerate it. So I'm going to zoom in. Here's the battery. This is looks like this, right? So this end would have plus charges, minus charges. Battery is full of something, so full of chemicals, some chemicals and chemical reactions in here. They create a potential difference between the two ends. Okay. If I remove a positive charge from here, chemical reactions are triggered to maintain the potential, to maintain this one to be still the same number of charges here, and then, so that there would be a constant potential difference from here. So it stays 12. Okay. So if you look here, the electric field from pluses to minuses, the electric field is this way, right? If you're trying to grab a plus charge and move it from here to here, so here's your plus charge, and you're trying to get it to here. But these pluses are repelling it. It's actually happy where it is, right? So why does it move from here to here? There must be so let's see, here's the charge. Right? The field, the electrostatic field is that way. So why does it move this way? There must be another force or another field that's this way, and that field is from the chemical reactions, or that force is from the chemical reactions. Similar to, I think of it like this, or the classic example people give is like if you're trying to ski. So you go up a hill, and then you ski down the hill, no problem. And then you can walk up the hill using your legs, or maybe use a ski lift or elevator or whatever. That's what the battery does. It takes you up. It takes you from the lower potential to the higher potential, and now you're ready to slide down and then repeat the process. That's what the battery does. Until it does. So, essentially, I really think of it as somebody trying to pick pluses and put them there. You can't do it by hand. It does it through chemical reactions. Okay? So the battery will provide you with a, can I erase this? So the symbol for it, it has this. Sometimes people call it, they use script E. It's called the EMF, electromotive force. Nobody likes that name because it has the word force, and it's not a force, it's a voltage. And it's in volts. Volts. I'm going to write 12 volts, but please don't think it has to be 12, right? You get batteries that are 1.5, right? Or 12, or whatever. 18, something like that. Okay. So that brings me to here. So this one is plus, this one is minus, this is plus, and this is minus. So the battery will charge the capacitor, this plate will become plus, this plate will become negative. Does it happen indefinitely? Do you keep piling up plus charges until you get an infinite amount of pluses here and infinite? No. When does it stop? Yes?
I don't want to answer that question, but I have a different question. So if there's a bunch of pluses on the big line side,
This one?
yeah, then I understand that like when it leaves, the chemical reaction is going to maintain the voltage, so replace it with another plus. But when it's leaving, you're saying it's going to that big line?
Yeah, this one.
How come the plus is going to another plus then?
Maybe when we answer the second question, might answer actually this one.
Okay.
Let's see. So, does it happen indefinitely? When does it stop?
When it reaches some sort of equilibrium.
When it reaches equilibrium. Okay, good. And when does equilibrium happen? So I'm looking specifically for the following answer. So let's say this one is 12 volts. when equilibrium happens, what's the potential difference from here to here? From here to here should also be 12. 12 volts. So let's see why that's the case. Let's choose a point in here. Choose a point. What's the potential difference between a point and itself? 0. A point can't have a higher potential than itself and not lower than itself. It's equal to itself. Okay. Let's go around a loop, a closed loop, and ask what's the potential change when I come back. When I come back, the potential change has to be 0. Okay. So let's see. It's called the loop rule. So I start here. I cross a battery. So I go from the minus terminal to the positive terminal. What's the potential change? In this case, it would be 12, right? If I go from minus to plus, I went from lower to higher, so it's plus 12. Okay, so plus 12. Okay. This is a conductor, so it's actually at 12 volts. This whole thing is at 12. It's equipotential. So equipotential until I get here. I cross from here to here, there will be a change in voltage. But I went from plus to minus, so the change is negative. So let's call it minus VC. So here's the equation on the right. The change from here to here is 12. And 12 is just a specific number to provide some context or some specific. Minus, I go from here to here, that's the voltage across the capacitor, and I put a minus sign. I put VC here with voltage across the capacitor. Okay? And then nothing, and I come back. So what should the total change be? 0. So I get 12 is equal to VC. So the potential difference between the plates must equal to the potential difference here. So I think to answer your question is this. We need to have enough charges here so that until the potential difference from the positive plate to the negative plate has to be 12 volts or equal to this one. If you get less charges, then you would have less potential difference, right? Because less charges, less electric field, less potential difference.
How did you know that it had to equal 0 to eventually?
Yeah, so
Is it because electric potential is a state variable? So you know that if you're at the same state, then no matter what you take to go there, then it goes to
in the context of thermodynamics, state variables, yeah. But here we're talking about like basically conservation of energy. So I asked, what's the change? What's the potential difference between a point and I will get back to you. Yeah, between a point and itself, and the potential difference between a point and itself must be 0. So when I go around and I come back to the same point, I must have this. I come back to the same voltage, so the change has to be 0. Similar to this. In the context of gravitational potential energy, I have this one on the table, and if I wander around and I bring the pan to here, the change in potential energy is 0. Yeah.
So for all batteries, are they considered closed loops?
The loop has nothing to do with the battery. It has to just be coming back to the same point.
Okay.
Yeah.
Will it tell us that it's a closed loop, or do we have to realize that it's a closed loop in a problem or like an example?
Let's do more problems, and then maybe that will answer the question. Yeah.
And then for this example, what does VC stand for again?
The potential difference across the capacitor.
Okay, thank you.
Well, okay. Yeah.
So like in the capacitor itself, are there actually like photons shooting from the positive side to the negative side, which is empty?
Yeah, this is empty space. Back there. Yeah.
So I'm assuming that like the current in the circuit is made out of electrons, not photons. So when you say that the flux is going to go to that side, so that goes the rule. Is if I were to visualize it from the perspective of electrons, would it be that this is positive and this is positive, an electron from here wants to go here to make it neutral?
Yeah, you
And
can
then
think
that
you're
is a positive charge?
Yeah, you're removing electrons from here, basically there. So positives going here means negatives go there.
So
We haven't talked about current yet.
Oh, sorry.
Yeah.
Okay.
So Yeah, so mathematically, a plus charge getting here is the same as a negative charge being placed on. Right, did I answer your question? Or?
Yeah.
Okay, I forget what the question was.
No, it was the empty space inside.
The empty space, okay, yeah. Okay, so, yeah, so for now it's vacuum here. So charges cannot jump from here to here. We'll discuss that later also. Okay. And then, talk about batteries. Oh yeah, now we're going to discuss how much energy does it take to charge up a capacitor. To charge up a capacitor. And then from the energy, I will talk about energy density. The energy density that we discussed about capacitors in series and parallel. Hopefully, we'll get to it today. Okay. So, how much energy does it take to do all this? Right? How much energy does it take to do all this? That's the question here. So, energy. Stored. So you start with the plates. Let me put them horizontal. Start them with the plates neutral, right? And you start placing pluses on here. Remove plus from this one and place here. So you remove one plus from here, you place it here, you get a plus, 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 plus. Eventually, this plate will reach a capital Q, and this plate will have a minus Q at the end. And the question is, how much work was done to do this, right? And the way to think of it is this. So before we reach here, before we reach this state here, so we had to get from 0 to capital Q, right? So in between 0 and capital Q, so let's call the charge little q. So let me erase this. So before we reach capital Q, the charge would be at little q, and here would be minus little q, right? That's the charge there. So what would the potential difference between the plates be if the charge is little q? Yeah, I think it should be, that's the right place. C is equal to Q over V, right? You're right. C will equal to Q over V. I put little q because we have little q now. Therefore, V will equal to Q times C. That's the potential difference between the plates. Q times C. So, how much energy does it take if I want to take a little dq from here? Here's a dq. Take it from here and place it here. By how much does the potential energy change of that dq? I'll call that potential energy change du. What would it be? How is it related to Q or to dq and the potential? V dq. QC? dq times 2q. Why would it be 2? It's 1 dq. I'm moving the dq here. Yeah.
Isn't it little q?
dq
DQB?
times
Okay.
Yes.
Could be like V equal Q over C.
Oh yeah, yeah. Yeah, you're right. I made a mistake here. V is Q over C, right? Yeah. It's Q over C. Thank you. Like this? Yeah. Right. Okay. So dq times V, and I'm going to replace my V by Q over C. So I get Q over C times dq. So U, in charging from Q being 0 all the way to little q being capital Q, is going to be 1 over C Q times dq, go from 0 to capital Q. Notice 1 over C comes out of the integral because C is a constant, right? If you construct a capacitor, it has the same capacitance. It doesn't change. And so if you do this, you get Q squared over 2C. Okay. Q squared over 2C. There are different forms of this, right? You get the letter Q, the letter C, and V. So the potential energy, you can write it in terms of Q and C. You can write it in terms of Q and V, and also V and C. You can write it in terms of. So there are other options. So I will show you what the options are. So I'm going to have equivalent ones. This is not the one I remember the most. I will show you the one I remember the most in a second. So let me write it. So Q squared, yeah, Q squared over 2 times C. Let's eliminate C and write things in terms of V. So what can I write instead of C, what can I write?
QB.
Q over V, yeah. V flips, one of the Q's cancels, right? And so we get 1/2 of what? QV. So that's another way to write it. And then let's do a third way. That's the way I actually remember. Let's eliminate Q now. CV, yes. What does it become? 1/2, yeah, CV squared, right? This one reminds me, what does it remind me? 1/2 CV squared.
1/2
Yeah,
MV squared.
1/2 MV squared. So that's why I remember this one. But they're equivalent, okay? They're all equivalent. Do an example, and then let's do a quick example here. We have so the example is this. Consider a 220 microfarad capacitor charged to 330 volts. Find so meaning how much charge is on this capacitor, and then how much energy is it stored. The capacitor is 220 microfarads, and the potential difference between its two plates is 330 volts. Find Q and P. I need your help with this one. CV for Q? So Q is CV. So 220 times 10 to the minus 6, right?
Yeah.
And then 330. So who can tell me what we get for P? For Q, sorry. Zero point
0726.
726
Yeah.
coulombs, right?
Yes.
I will write the word coulomb. If I write C, it might appear capacitance. Okay. Sounds good? We can do U now, right? U is 1/2. Well, you can actually choose any of these. This or this or this, up to you. I remember this. This one is the easiest one to use for me because I just remember it. So I will use 1/2 CV squared. Again, feel free to check all the other ones. They're the same. U is 1/2 of C, which is 220 times 10 to the minus 6 times B, which is 330 to the power 2. This one I do have the answer to. It should be 12. Right? 12 joules, more or less? I think it should. Oh, it is, okay. Alright, so I rounded. Alright, so 12. Yeah.
So the potential energy equation can be used for any capacitor? The 1/2 CV squared?
Yeah.
Okay.
Yeah. We didn't make any assumptions about the specific capacitor. Yeah.
So since U is similar to kinetic energy, is Q similar to momentum?
Q. You said Q.
Yeah.
Q is just charge. If you want to make analogy with mechanics, usually Q is M, is the mass.
Okay.
Okay, let's see. We got that. Now, the energy stored in the electric field. Energy stored in the field. So that's my next goal. I'm going to do it in 2 ways, and then we will move on to this topic. Energy stored in the field. Okay. So you have you have one capacitor with 2 plates. We're going to look specifically at the parallel plate capacitor. So here is the plus, say. Right, this plate is positive. Its area is A. And the area of this other plate is A, right? Is also A. And what I actually intend to say is here is plus Q, and here is minus Q. That is not plus Q. Minus Q. Okay. Imagine, right, we're pretending these are infinite sheets, although they are not. So, in that approximation, there is only electric field between the 2 sheets, right? Remember the infinite sheets? There is no electric field outside. Electric field is only inside the 2 sheets. So we just have electric field here. So the distance from here to here is Z. And, okay. So the potential energy is U, 1/2 of the capacitance times the potential difference between the 2 plates squared. So 1/2. For parallel plates, it's epsilon naught times the area divided by D, distance between the 2 plates. And then the potential difference between the plates is the electric field times